Okay, so hello everyone. Can you hear me online? Is everything connected well? Okay, I hope you do. And I hope you can see the screen as well. So it was, by the way, a very nice day yesterday. I could see the temple, which was very interesting, and a part of India. That's why I had a break, but we will cover those remaining hours today and tomorrow. So what I want to add first is 2 or 3 slides on material that is additional to the previous discussion. First, because I find this paper is quite interesting, it relates first to amount of data we need to use for training. So this is very new analysis by the researchers from Germany and from USA. And then they ask the question, if we keep adding more and more data to train LLMs, bigger and bigger LLMs, high quality data, when will be the time when we sort of start really needing synthetic data or some other kind of data, because we'll be lacking that enough amount of data. And this study is simulating the current speed of growth when it comes to the necessary data for training the models. So you have Llama 3, Falcon, and so on, extrapolating it, but also considering essentially what is the increase in the number of internet users, so how much data will be there on the web predicted using some simulations, social study simulations. Taking all this together, they say that around 2026 to 2032, well, perhaps more towards that end, around 2032, let's say, we will be using as much data for training these models. If, of course, everything goes in the same speed as we have now, we'll be using that much data as there is available data on the web, right? So you see that at some point we will need to do something. Maybe this prediction is a little bit too fast. Maybe it will come later, but at some point we'll need to think what kind of other data we can use if we want to achieve that speed of increasing accuracy of the models. We'll need to use synthetic data. We'll need to perhaps use some kind of knowledge transfer technologies or technologies that will somehow solve this issue of the lack of high quality. Of course, the web is large, we can use it, but as you see through these simulations, at some point it may not be enough. Okay, and now the last slide remaining to the previous content that I want to add is about selection of the examples for LLM when you use few-shot learning. And here we proposed this year so-called pedagogy-inspired selection of examples for in-context learning. And the idea was how to find good examples. If you have a pool of examples for good learning, I mean, good answering questions, let's say, successful, and how to combine these examples. And then we propose this solution here, which is looks a bit complex, but actually it's not complex and it's based on how humans learn. So imagine that you have some questions, QSR questions, in a pool of data with their answers, of course. So the answers are given here. And then from this pool of data, first you're sampling a question and asking LLM to provide an answer. You got an answer, and whenever the answer is correct, I mean, it's the same as ground truth, you consider it as solved, this question. When the question is not answered correctly, you consider it is wrong, and then you store it in a challenging data pool, right? So we can compare with a ground truth, and whenever answer provided by LLM is wrong, well, then it stores this question in a challenging data pool. And we do it sampling all the questions, but later what we do, we are actually making a chain of questions and seeing if these examples here, if you, let's say, give one example, like in a second round, and will it help to answer some challenge, some data again? And if it's answered, then fine. We consider those questions with its answer as good one. So starting with one question, so 0 shot, we are now going to the 1 shot, then we are going to the 2 shot, and up to, I don't know exactly, but I think it was 5 or so. And then we are trying many questions, and you see that when the model will have more examples given to look at, usually the probability of answering the question will be higher, especially as all these examples have been already correctly answered from the previous round. So we know what the model knows. And essentially, we are taking the kind of known by our model a question, an answer is produced, and so on. And finally, we take these longer chains, but now we pick up data, well, some question that was still in a challenging data pool that was put, and hopefully this will be answered because you have many question answers that were, many question answer pairs that were already known to the system. So these are kind of well understood, and we hope that by these good examples that the model knows about them a lot, knows how to solve them, this challenging data can be solved. But now we are actually giving this challenging data pool, we are accepting some chain. So this is good chain because the answer produced for this challenging question is correct. But for the bottom case, actually the chain didn't help to answer this challenging data, challenging question. So this chain is rejected. And in the end, we have a couple of chains of example questions as a kind of good few-shot learning material. And what we do later, we are at the inference time when, let's say, a user is typing new question, the question that we never have seen, right? Because all this was from a training data. Obviously, we can control it very well and arrive at such a chains of examples. But when the user now types any question, what we are doing is we are first using first chain that passed the exam. This was a final exam stage, by the way. And then try to answer this question from the user. So imagine now this one would be from a user. And then we take another chain that also passed previously the final exam stage and again try to answer. And then we have a couple of answers for the same question because each time this new question from a user was always contrasted or equipped together with some example chain. We get a couple of answers and we do majority voting to pick up the best answer, right? I mean, the most common, basically. And all this style, you see, is a lot of steps, but it can then be very quickly, especially as this is offline phase. So on this quiz phase, you can essentially do it, at nighttime if you want on a certain type of data. Of course, it's anyway fast, so it doesn't really matter. But then it's prepared. So when the question comes from the user, we just use these example chains that are verified as has been progressively established as a good ones, and then majority voting is taken. And the idea is that this is coming from Brunner's spiral learning theory, for humans, of course, that was invented, and that the learner should progressively learn more and more difficult things by understanding certain things and using those understood things, well understood things, to answer the next questions. And that was found to actually perform quite well on different data sets, from mathematics, from common sense reasoning, from some symbolic, not sure what this data sets, I don't remember anymore, but you have just the average accuracy here. And you can compare a zero shot when you don't use any examples at all. You can compare the case of zero shot, but chain of thought. That means a string which says, please think step by step, or reason step by step without any examples. This was, I think, another style of prompt engineering. But here we have normal few shot. Here we have also extension of a chain of thought, that is automatic chain of thought. I think maybe the model is producing its own reasoning and then helping itself. Self-consistency, I think, was discussed last time. But here we have this chain of quizzes, the proposed idea, and you see that we managed to have good results on many data sets. Of course, the improvement is not that dramatic, well, not always at least, because you are reaching already quite high values. So then usually to get strong improvement when already accuracy is high, let's say from self-consistency or so, it's not that easy. And there were experiments we've done with GPT 3.5 Turbo. So what is important here, I don't want to ask you to remember these things. I just wanted to show you these options that you have, the complexity of choosing examples, and examples not randomly chosen as usually is done, or based on some diversification strategy just to have different examples, but progressively picking up examples that help to solve more and more challenging questions, and having some kind of good verified chains, and then majority voting is here, right? So these are many steps you can do for in-context learning. And also, by the way, we studied what is the optimal length of this example chain. So how many these question answers here should be an example, and it was found that 10 is okay on different data sets. These are 3 data sets. 10 is already good. And then how many examples? No, sorry, this is different. So this is, I think, the number. No, yeah, how many of chains is here? So we need 10 such chains, but each chain is enough if it's already, let's say, 5. So it doesn't need to be that long amount of question answers here to have good effect. But we need at least 10 such chains, and let's say 5 length in each one. If anyone wants to ask questions, just let me know if something is unclear in this strategy. And then, well, this is just one solution of how to pick up good examples to solve any new question coming. But it goes into this style that we can manipulate many things and do it, verify the performance, and again, iteratively. This can happen actually, as I said, offline or even very fast, so user will not feel anything. And also, this majority voting style is good, I think, because even though you have different same model, but the same model is equipped with different evidences to support its own thinking, and then given different answers. But if you combine them together, then you are likely to have a good answer. Okay, and now I want to talk about name entity recognition, because later we'll go to some temporal information processing parts. So this will be continuation of NLP discussion so far. And name entities are very important for any analysis of data, especially news data, for building knowledge graphs, and so on. Name entity, of course, means something like person name, like Janet, or organization like Innsbruck University, or a location like Colorado State, or some city like Patna. We want to capture those automatically, and then later find the relations between such name entities. So it's a well-defined task which exists for many decades in natural language processing, and with many applications. The community usually cares about 3 major types of name entities: persons, locations, and organizations. Just like here, organization means does not have to be some kind of like university organization. It's just an entity that is collectively, let's say, a group of people, like company, like some government or organization, like some voluntary organization. We might have a miscellaneous group as well, but these are the most three, and most common three. Most of the solutions just work on those. Of course, we can have extension of the classes like those here. Let's say time, maybe we want the money. We have data sets for these and tools for that. And of course, domain-specific name entities, that is not in a mainstream code, but you might, let's say, wish to pick up some protein names or genes from scientific papers. Then you need a new training data or already trained detectors for that. Like here is an example. I'm not sure who is from biology here or medicine, but you would probably understand that these indeed fall into something like protein or DNA or a cell line, very domain-specific types of name entities that someone might care for, and you have some data for that as well. And here another types of name entities. As I said, this people, organization, location is the most common, but then many times we see some more extensions. I mean, this is not domain specific, but for example, this geopolitical entity is not geography, but is some kind of a state. Like here, Palo Alto, although this is a city in USA, but in this sentence, Palo Alto exists as a kind of government of this state, well, not state, this city, right? So it's raising and facilities of bridges, buildings, and so on. Well, many conventions, but we will care mainly about the three: people, organization, location. Here you have even fine-grained. Someone might go into more detailed things, not people, but also is there a best businessman or actor or musician or scientist. We want to classify detected name entities into such groups, right? But let's see now how this all could be done. So what we can do, of course, is to use some existing list of name entities, so-called gazetteers, place names from websites like GeoNames. We can use some list of genes, proteins, depending on a task setup. But the problem is that for the zip flow, we know that these lists are never exhaustive. There will be always some new coming name entities with very small frequency initially and perhaps growing or perhaps not in their commonness. But there will be a lot of those not on our list. Through the zip flow, essentially, where you have such a long list, long tail, where none of the corpus that you can build will always capture all of those. So yeah, this is always a problem, and ambiguity is another problem because we need to distinguish whether Washington in the text is a person or perhaps a US government or a state and city and so on and so on. But a name entity recognition task typically means find a span of text that constitute proper noun and then detect the type, like out of these three types, like person, location, organization, perhaps more time, money. Well, it all depends on the setup, but these two, first you need to find, and second you need to detect the type. And then, many tasks, downstream tasks can utilize it: sentiment analysis, question answering, especially linking entities. I will talk about it soon. And in general, understanding of natural language could benefit. I said many kind of types, but now I want to show an example. And what you see here is a labeling given by adding these small types of name entities in a blue color and underlining in a bold font what is the span of text that a name entity falls into, right? So the system should recognize United Airlines here and give a label: organization. Friday is a time. We now care about the time in this setup, money, and so on and so on. So this is already quite useful because you can collect all the mentions of companies. You can count how often, let's say, United Airlines appears with perhaps this Tim Wagner or someone, and have some knowledge already, which is very semantic because it's focused on particular instances of things, not abstract things, but very concrete. And that's what often human cares about in a text, about name entities. Now, segmentation, ambiguity. Why is it hard, right? So in a part of speech tagging, which we before discussed, where usually, well, always one word was one part of speech, like adjective, noun, verb. Here, the word may not be just individual, because we might have, like here, American Airlines, or it could be much longer than that, 3, 4 terms. And this span can have varying essentially length. So this is a difficulty. We need to know where to stop and of course, where to start. Once we know where to start, where to stop, where is the end of the name entity. And so find and segment these entities. And this type ambiguity, as I already mentioned, is a problem. Washington here could be in all those different types: geopolitical entity, location, organization, and person. That is, of course, harder. And I also want to mention the issue of hierarchical labels. If you have University of California, we would agree that this is organization, but well, some kind of attentive name entity recognizer might say there is a California detected here, even geopolitical entity, not location. And then all this is also organization. Do we want it or not? That's debatable. Perhaps not, because this is already something, longest and standalone. We don't care about California so much here in a text, but about the University of California. So often we don't care about those nested issues and consider that just the longest, a flat, but the longest case. However, that's not always working. If you see this John's mother, yeah, maybe someone might say we want to care about mother of John only, but John here is also emphasized in a sense, much more emphasized, let's say, than this California here. Well, it's all debatable, but you see the problem that there are nested entities as well, and we need to somehow make a decision. Are we caring about them? Do we want to detect them, or we just skip them? Okay, but how to simplify this problem? Because as I said, the span of text can have different tokens, a different number of tokens, and that may not be simple for classifiers. We want to do classification task, and we want to basically simplify it. So we want to turn this problem in a sequential problem, just like part of speech tagging, where each word has one label only, right? So United will be considered separately with one label, of course, organization, airlines also organization, holding also organization, but not the span, because this makes it too difficult for practical scenarios. So there is a scheme, tagging scheme, which is quite useful, and it's called by.io, and you will find it in not just name entity recognition, but in many tasks to classify something from text, to extract something from text. So it's a kind of versatile tagging scheme, where you actually have, in a most simple version, you have the label called beginning of a person, inside person, outside, then beginning of organization, inside here as well, and outside, and the same with location. So you actually have now how many beginning? You should have, I think, 7 new labels created according to this scheme, rather than just a 3-person organization location. And then you can operate on individual words. And it's important to indicate where is beginning, where is ending. Well, at least where is beginning, because the ending could be understood from this combination of inside and immediately followed by the outside tag. So the model will, the classifier with this labeling will learn all those patterns. And the beauty of this is that now we are tagging each individual word, making it as if it would be part of speech tagging tasks, so much simpler. The fixed set of labels per each token, right? As I said, probably 7, and so on, right? And here is Semantics, B means begins, inside, outside, and we ask some human, typically, to make these labels so that later the model can learn on this data, right? So we need someone to do this labeling. Maybe these days we can ask GPT-4 for that, but yeah, typically it was done asking humans. And now the number of tags which you will have is governed by this equation, 2n plus 1. Well, n would be depending on what was the n? I think n is the number of a name entity types. So we have person, organization, allocation. We have 3, right? So 2 multiplies 3 plus 1, as I said, it would be 7, right? 7 we have. But imagine now that you have also this time, you have also this money, this date, as it was shown sometime before in the slide. So slightly longer set of entity types, then the number of tags will be, of course, larger, governed by this equation here, but manageable. And here is an example of tagging that we would ask human perhaps to do it first for a machine to learn, and the machine would be asked to recreate such a tagging, right? So initially you say this Matel is that's probably Indian person, right? Matel, I'm not sure, maybe not. Yeah, it's organization, beginning of organization, right? But then let me see, why is it here is inside person? Okay, because it seems that, yeah, it's again, we could say that it's a hierarchical, right? This is organization, but this is a person, although this beginning here for A, I would rather, yeah, contest it. But altogether, if you look the daughter of a Mattel founder, maybe this is one person, right? So, well, perhaps this D should not be indicated. Well, someone made mistake, in my opinion, here. In this example, we should start with daughter. But altogether, this span is indicating a person, right? If you just disregard or maybe shift everything to the right. Well, maybe this example is better. So you have also many variants of this BIO. You might have a simplified case where you only care about inside outside, so you don't care about the first token. You don't treat it in any special way, right? It's just always inside, outside, inside, outside. You might have even a special emphasis on this ending and starting. No, sorry, S is not starting, beginning, B is starting. S is a single instance, like here. S location means Chicago is just one token. That's why we use S for indicating. And different standard you use, of course, classifiers may need to care about more classes or less classes, but always the beauty here is that from the spans, varying length of spans, we always go to per token decision by a classifier, which is simplifying the story. And I wanted to also show you one example of a tool which is called Docano for making these labels. If you have a new task, let's say extract something from a text, it doesn't have to be name entity. It could be, well, some, I don't know, some sentiment words or whatever, or perhaps a very rare type of name entities where you don't have a data, or perhaps a language is like here that is not so well resourced. This is a Polish language. I'm from Poland originally, and it's a Slavic language, so similar to Czech, to well, Russian as well. No, different, because we use different characters. But here, what we actually use the tool, and I want to show you how this tool works and how easy it is to just use it. So you have a text, you have some labels here to choose from, and you just click on a word. And I think, yeah, you first click on a label and then click on a word, and the word is becoming labeled by whatever you provided first, decided first as a classes, and then you can export it to JSON, export it to whatever format you want, XML and so on, and utilize it for some classifier. But this is what a human would look at, graphical user interface, choose an articles here. This is an article choice, and then click on those, and then first highlight which one you want, and then click on which words, and then move to the next, to the next, to the next, and label in this way. What we were labeling here actually are diseases. So we care about very domain-specific problem, labeling instances of outbreaks of diseases. So this is name of a disease, and yeah, maybe some human, I think it was even me, did not do very good labeling here. I don't know why is it repeated here everywhere. There was something with, well, it's not that maybe important, but you see how easy it is to do it. And one problem here, I think, in the design, if we just talk about user interface design, is that beginning of disease is separated from inside disease by another token. It was so confusing once you select first beginning of a disease span, and then you want to select next following one, and then you have to not look at the next, but somehow jump it. When you do it so many times, it was just a small issue of arranging these labels could have a meaning, speed up and less confusion. Why we even did this kind of study, that was in 2020. So we had this project on multilingual epidemiological text classification. The idea is to have a system, and that was all, you know, in the times of COVID or before even. The idea was to have a system that will continuously scan newspapers, but we are talking not about English newspapers, about local minor languages, like probably some in India, but definitely in Africa, we have many languages that are underrepresented. And then trying to detect, well, some metadata like time, but anything, what kind of disease, how many patients, quickly before national news will pick it up. So we extract it from local languages, and then database can build it and map perhaps where is Ebola in Africa and what time. And this was multilingual, because many languages, actually it was low resource languages. We studied, as you see, Polish. We didn't have many resources. We studied also, I think, Russian in addition to English, and built such a classification system. But that's not what I wanted to talk mainly. I'm just wanting to conclude this part, say that for name entity recognition, once you have this labeling, you can use essentially any classifier. Like most likely these days, you would focus on BERT and train a BERT to detect those instances, labels in a text. You can use RNNs or in general any other type of transformers, LSTM. And that's probably what Professor Sriparna was already teaching yesterday, at least for some of you. And you can use all their methods like hidden Markov models, conditional random fields, and some more explainable, easy to explain, but not that powerful classifiers than, let's say, more neural network-based ones. And now I want to go to the next part, which is information extraction. That is building on this name entity recognition. And here we extract something more deeper than just essentially relations we extract, but deeper than just mentions of entities, to organize information, to build some database from text, useful for us. For example, we want to know where companies have headquarters. So whenever we have a company, we look for, in the news perhaps, we look for any nearby information where it is headquartered. And it is mentioned often in the news. Or any other relations, who did something, what, to whom, to when, we can try to extract it. And you see this is relation now, not just mention of some name entity. Perhaps a more domain-specific example would be interactions of drug and genes from literature, more complex, obviously. And here is an example of a, BERT employed to detect types of relations. Once we already indicate there is a name entity, there is a name entity in text, and there is another name entity in text, and they are close by. Let's say you set up some distance to expect there will be some relation between them, like was born in. And we first, of course, employ name entity recognizer to find all those name entities as we studied so far. But we later substitute their particular name by a token, general token indicating type. This is done in order to not let the model too much focus on one particular name entity, like, oh, for Japan, maybe it's this versus Australia. No, rather operate on the higher level, not so specific to particular instance, but specific to type, right? So any relation between persons and locations. And we classify what is this relation by using token. This is a standard way of using CLS token, which is the initial token of the paragraph, which is supposed to represent the semantics of all these texts, including also information about this person and location. We have linear classifier and a set of classes where each class would be relation. So let's say this data set employed here have 42 relations. One of them is was born in, another might be married to, or another is CEO, or studies at, or works at, or whatever you labeled in an existing data set. It is one of the standard relation extraction data set, which have 43 labels. I think maybe the additional label would be there is no perhaps relation or unknown. I don't know why, but it's 43, although we have 42 here. And yeah, so essentially, I would just to always start at least with BERT, with data set that is properly annotated, and of course labeled. So we need to say that okay, this was born in, will have a label of birth, right? Another instance will have another label, but this will be, of course, here during supervision utilized. And now I will, let me check what time is it. So do we need a break or not? Perhaps, maybe not, but I just need to get the idea. Oh, no, definitely it's still early, so we can continue. So I want to talk about things about temporal, because the whole lecture is about temporal information processing. So from now on, we'll be focusing on a time aspect of all this text manipulation and information retrieval. I want to just mention as a background that time is important. We have time as an aspect, key aspect of narrative stories, events, helping them to stitch them together, to understand them by human. For images, you look at a certain image differently once you know when it was created. Well, intuitively, we know that time and space and location are two very important axes of the word, well, of text as well. And time can also determine if documents are relevant or not. So for search could be useful, and all those understanding related applications. And the community had so many other problems so far, this NLP and IR community, that in my feeling, the focus on this temporal aspect was not that high. But now I see so many papers appearing that manipulate some temporal signals in text that I think it's a sort of increasing this focus. But yeah, let's see some instances. This is from, I think, news on the left, Wikipedia, but it's called as a narrative document. And perhaps this also comes from Wikipedia, but it's more focusing on a person. So biographies. And we'll be now studying different characteristics of different types of documents when it comes to temporal information, temporal signal. So you see here some temporal expressions, right, and also here and here. And now the task for a so-called temporal tagger. So, well, tagger, like name entity recognition tagger we studied, but now we care about only temporal signals. So the two tasks would be first extraction of temporal expressions. Sorry, just like here, find where they are, these temporal signals. Obviously, we have publication date of this article, that's one temporal signal, but then we have tonight, yesterday. I increased the size here so they are more visible, but you see they are scattered, providing temporal timeline of narrative of this document. we need to extract them, and this is the first task. And there are different types of temporal expressions that we may need to extract, organized by some standard, like this is a time markup language, well-known standard by a US researcher in Brandeis University provided. It divided the time expression into dates. Of course, date may not lack sometimes year information or lack a day. It could be just months and yeah, and the year. Anyway, durations, times, where the time information is provided. Well, in addition to date here, but I'll be more specific on time, and the sets. This is how they divided different temporal expressions in a text. They want to detect them, but not only detect, they also want to, this is a second task, important task, normalize them, these extracted expressions. So tonight, yesterday, okay, it's useful for us, but we not want to know exactly what it means tonight and yesterday or earlier today, how to map it into timeline. Like this one, we could map. This one, of course, is fully specified, so the mapping here is obvious. But here, yeah, here is actually not obvious, because next month you need to understand, looking at the flow of the semantics here, or just looking at least at the timestamp. So it may not be obvious that clear always how to normalize expressions. For explicit ones, as I said, it's a rule base. It's easy to normalize to some canonical form, like this one, right? Canonical form. For relative ones, like 2 weeks ago, yesterday, we need some reference time. We'll talk about it later to anchor these on the timeline. For implicit ones, the name is implicit because it does not say exactly which day it is, although you can typically map it. Typically map it, but you need some additional knowledge, a calendar, for example, and to check when Christmas was in this year, or this Columbus Day. But it's possible to handle, though. Them, the toughest are those underspecified, where, yeah, they need reference time and something more to really understand them. Maybe common sense reasoning, how long actions typically last, and so on. They are a bit harder. But I just gave you a snapshot of types, different types, and how easy it is to normalize them. Of course, we may have different languages, like heute in German, hoi in Spanish. We might have these relative ones, like this and this, that I always need to relate to something. But anyway, ultimately, we want to always map them on a timeline, because then we can do something, summarization or mapping on in visual way, progression of events and so on. Of course, information in time is also hierarchical. So you have a year, months, and a day, part of it. So this is nothing really specific, right? Again, a slide showing hierarchy from a decade. We go to years, then quarters. Especially quarter is important when you handle financial documents, right? And often you have some mention of a quarter. Then goes into months, days, and even the time. So different granularities, but they are hierarchical, as we see here. Altogether, these temporal expressions are a special type of name entity. You even have seen in the previous slides, some name entity recognizers were considering time as one of a name entity. But if you want to make it more precise with a good normalization, you typically use specific temporal taggers that are focusing only on temporal information, but really deeply and doing it accurately. And yeah, we also need to consider our modifying signals that may appear before those temporal expressions, like before, during, after, between, because they have a huge meaning and can impact the meaning quite much. So here is, I think it's a news article, yes, news article. And you see those in temporal expressions. Well, this was 2000, the entire year here. Months here mentioned, we don't know which October it is, so we often look into the timestamp of the article, same as another Thursday here. Every 10 years, it's a kind of interval, a set, so repeating periodical expression. And then you can even, of course, this is another story, but you can reason on actions once you have next or nearby temporal expressions. You can relate and say something that this leaving was about October and this publishing was on Thursday and so on. So this is a news article. A narrative document that would be, I think this is taken from Wikipedia, but it tells the story of a Soviet invasion on Afghanistan. And you see also temporal expressions, but they are kind of different. They are more explicit. We don't need so much to utilize this creation time as it was in news. But sometimes we may need, of course, but often to disambiguate some implicit expressions, we just look at the nearby explicit temporal, right? So in the morning is defined by December 27, and December 27 needs to also look into this year because it's, well, it's not specified at least here. But we don't use that much utilization of this document creation time as it was in the case of a news article, right? And now we have tweets or short social media strings. And here, first of all, we might have, as you already noticed, a non-grammatical or not that commonly used, at least in my neighborhood, social neighborhood, expressions like last night. But when it comes to referencing, or this tomorrow, it comes to this referencing, we typically utilize very much creation time. So creation time is a king here in this colloquial text. They are very short also, which brings difficulty. You need to properly understand every word here, while in a longer text, you can be a bit more lax. You still probably get a meaning of temporal expression, but here it could be just 2 or 3 words sometimes, and we need to be paying attention. But typically, well, yeah, the creation time anyway. And domain-specific text. By those, I mean some medical documents, let's say government legal documents or scientific documents. Then typically the publication date does not matter so much. Just those inter-text relationships matter. But often these are more like intervals and periodical expressions, not exactly point. And there might be some time point zero a case where, you know, because it doesn't anchor everything to one particular time on a timeline, but it anchors to some time point zero in the whole story, how experiment was done or what to do when certain action initiates, and then subsequent years, what is in the legal document allowed or not allowed is specified, but this time point zero is there. So anyway, we have many resources for this. We'll look into them a little bit, which are already annotated by the labels. So the temporal expression is indicated in a text and also normalized. So we have these 2 tasks solved, as I said. We have some temporal taggers. Idle time is done by one of my friends from Germany, and it covers many different languages, but I think maybe not Hindi. Arabic for sure, and Chinese, but maybe not Hindi. So, well, if there is none, then this is again low-hanging fruit to do something, and something that could be, or not, doesn't have to be Hindi. It could be one of those still very popular languages, but not that much studied, that perhaps doesn't have temporal tagger, which time is important and could be utilized. But often just to design it, you don't need to do too much, let's say, clever solutions, because you look at the similar languages, maybe how it was done in, I don't know what would be similar for Hindi or Bengal, but yeah, maybe even Arabic or maybe even European languages, and employ similar things, essentially labeling, training birds, perhaps looking into some rules, depending on the language. Anyway, as usual in NLP, most research is English and most research is a general domain. And that's how it comes in NLP. So we have also many opportunities to do, let's say, Hindi but medical text or Hindi legal, and then all those combinations, there's a lot of specificity here. Now let's see examples of some corpora. Time bank, so very early corpora from 2003, annotated news articles. We see that mainly we have dates, a little bit durations, set or time, those 4 types of temporal expressions, but predominantly dates are in news, right? This is a news article data set. Out of all temporal expressions, more than 80% are just indications of date. If we look into those other types from the viewpoint of normalization, we see that many relative ones are underspecified. So this is a challenging thing. We need to always do those relativization steps. If we look at Wikipedia articles compared to the news, we see that that's maybe not that different. Maybe perhaps more dates, a bit less durations. But here, on the types of challenges in terms of normalization, we have slightly different. We have more explicit that it would be in the news, and more underspecified. So you see that the genre of a document has a big impact on distribution of those types and challenges related to normalization, normalizing these expressions. You need to use different techniques. Here a summary of what to do with news and narrative documents. I mean, not what to do, but what are the characteristics and the problems. As I said, news document creation time plays a crucial role. Many relative underspecified expressions. In narrative documents, we have many explicit expressions that are independent of document creation time, but the text can be long, complex temporal discourse structure, and so on and so on. So the challenges also are slightly different, but we may not need to go into that level of detail. Here, for SMS, short message service, short messages, you see also slightly different. Time is now more important because this is very timely medium. You issue those a couple of times a day, probably, typically. So time is important, not surprisingly here, date less, and others like that. Relative things are very common, underspecified, requiring some external knowledge. Expressions are also quite many. And the last is scientific type of documents. This blue dotted here, let's say, or I don't know, hashed maybe, how to call it, visualize things. The least number of dates, because it's scientific. It's more like some experiment or description of a procedure. And durations, you have to do maybe for 2 hours this chemical reaction, then 1 hour later, and so on and so on. And then sets how many times periodically you do things. And another challenge is here. So the picture is very much varying depending on the type of a document, as we see. Now we can also summarize colloquial text versus domain-specific text, noisy language in colloquial text, not many explicit expressions. People are lazy, don't want to type fully explicit date, just tomorrow, TMR, or something later. Hoping that by the time context, by the overall discourse context, respondent or whoever you converse with will understand anyway. Spelling variations, non-standard vocabulary are challenges. And well, missing contextual information. Sometimes it resides on what is the relation between two people, and we cannot capture it in any way. And this domain specific or scientific, there is some local time frame with 0.0, as I mentioned before. It doesn't have to be anchored on actual, world timeline, and many other specified expressions are a result of relative expressions. A common approach is to temporal tagging, quite many rule-based, I would say, because it's a bit less variation that you would consider any name entity to detect. There are some concrete rules we can benefit of. If not just rule-based, we can combine it with maybe machine learning or as a hybrid or semantic parsing. This is for extraction, this is for normalization. But the rule-based approaches, I would say, are not that uncommon for this task, as opposed to other types of detecting something from text, where machine learning is much more common. And here we see IOB classification. Before I call it BOI, but it doesn't matter. It just matters that we have three elements to care: beginning of temporal expression, here 2 years ago, beginning, inside, and outside. And there is only one type. We only care about temporal expressions, so not locations, organization, and so on. So this BIO or IOB in this case would amount to 4 different, am I right? No, 3 different, 3 different basically labels, O, by, and I. And that's it. And then you can train classifier to detect in a raw text for any token, is it O or B or I, and now detect these temporal expressions. Okay. Now let's say we have some detector, we have the, let's say, temporal tagger, how to evaluate it. This is actually Timex 3 standard for labeling documents, manually done by some humans. You see that March is annotated in temporal expression about 2 years ago. And let's say that this is a gold data, and let's say our system provided this outcome. March is okay, but 2 years ago, this about was missing. Well, people may argue, is this really temporal expression? But it should be maybe considered. Well, depends. We always look into gold standard, and some humans said that about here is really important. So now we evaluate it by 2 ways. Of course, we have all these true positives, false positive, true negatives, false negatives, strictly matching things. We would say true positives is only 1, March is good, and false negative. So basically you are penalizing this case where about is missing. Then you say what is detected here is basically, what is detected here 2 years ago is basically wrong. It is not what it should be, so it's very strictly considering, and you will not have a hit, and you will essentially have lower score, but you can do also relaxed matching, so saying, yeah, there is some overlap, that's fine, and you consider both of them as true positives in that case. So it depends on this strategy. We may use both evaluations and report both results. That's often, if none of the metric is perfect, that we often return a couple of metrics in NLP to have a broader picture.
But is false positive will be 0?
Yeah, I'm just also wondering myself why.
Some should be 2, like we are only 2%.
Well, wait, because maybe this about was considered as not labeled, right? And then there was a false positive, so wrong positive, and false negative. So it's just not shown here. Maybe it's better to show later as a separately. And that was about detection, right? So we did detection, but as you know, the system is responsible for typically for the 2 tasks, detection and normalization. So we would need to perhaps return 2 things, the normalization separately and detection separately, but it's a sort of, what someone might say, a pipeline case. Bottleneck. If you don't detect something, then you cannot normalize it, obviously. But you can return them separately or consider jointly that you care only about correctly extracted and correctly normalized cases, and then calculate metrics on that, perhaps at 1 score metric. So it's combination. you need both to be properly done in order to claim success. Yeah, it all depends, as often in NLP, on a convention, on how we see the problem, how important is disentangling or combining these two tasks. And here I want to tell, in this context, about one of my past researches that I did, and that was actually 2015. And it was done on a Twitter when Twitter was accessible in a sense of, yeah, you could, I'm trying to shift this, okay, where the Twitter could have been crawled for free. In Japan, I was at that time, we collected tweets from Japan, well, in Japanese essentially, and we collected tweets from US, but now I'm thinking that they actually were not just in language, they were originating from those two countries, because at that time it was possible to specify a location stamp of a tweet. Some people had it, not too many people had this option on. I think it was just 2% of Twitter users, but still we could collect many millions of tweets. So we were sure that the tweets originating in Japan, originated in US, in total 158 from US, and Japan was less, I don't remember exactly. But after we extracted any tweets that contain some time mentioned, the numbers were smaller, but not too small to do nice analysis, like 4 million tweets with any temporal expression from Japan and 30 million tweets with any temporal expression in US. And then we proposed to map this information somehow to draw interesting conclusions. And here you see a mapping. So first of all, we were crawling data from September 23 up to January, I think, 20 in 2014, a year before publication, if I recall well. And this white period here indicates unfortunate problems with crawling at that time. Whatever server crashed, there was my Japanese collaborators who did the crawling. I later joined to analyze the data. So we don't look into these white periods. What you also have is beginning of the months and end of the months by the solid line, right? So it's here we have October, we have November, we have December. We have also beginning and ending of every week, right, by dotted lines. And that's all for these fixed things. And then what we did is we organized tweets by timestamp. So the axis X goes through the timestamp. And we organize into those pointing to future and those pointing to the past as extracted from tweets, right? And then each square here denotes the intensity. This is a time point, essentially. Intensity, so the number of tweets that somehow on this particular day, because it's day by day crawled, right? That at this particular time, people referred to this temporal point, right? So they referred, let's say, with certain intensity 3 hours later, or 7 days later, or even a year later. And this is a logarithmic time scale, something very counterintuitive for us, right? When we show things, and timeline is always X axis, but always linear. Here is actually axis Y, and it's logarithmic. But if you think about how people refer to the past and future, it is also logarithmic in a sense, right? When we talk about distant past, 3 centuries ago, we often don't pick up a day or a time because we forgot it even, or are not sure about it, or we just don't care, which is more important. We just care about the year, even probably century. I was visiting the Museum of Bihar recently, and then everything was in a centuries because it's an ancient time and very, very long compared to Europe, like 5 centuries and so on. So we decided for logarithmic timeline to have everything in one view, of course, properly normalized, because one dot here now is embracing a couple of days, and one, of course, square here is embracing just minutes. So it was all properly done. And here is amount of future, aggregated amount of future, depending how far you look into future, and aggregated amount of past. Obviously, these are social media tweets, so people talk about very near hours. I will go shopping 3 hours later, or I will meet Jack tomorrow, and so on, as well as past. we found more about the future than about the past, but it was mainly just because, it was a little bit here debatable how to put certain very close minutes into future or past. It was not always clear, so we didn't really claim this difference as very important, this initial hours difference, but overall decline was important. There was kind of also logarithmic. What we found actually more important is these lines here. For example, let me come back. This line, there is, maybe it's especially more visible on the past. So there are these lines which are week lines, and there are these longer lines that are months lines, here and here. Essentially, people like to refer to the beginning of the month and end of the month, right? I will do it in January. I will do it after January comes, or I will do it. So it's kind of, and the closer you come to the end of the week, then this line is curving, because then you are, talking only about a day later or hours later. Of course, there were some variations like before, after, duration. We didn't manage to properly handle those because of the sheer amount of tweets. But there are certain regularities based on calendar effect that we could draw that are here. And then Christmas, because people talk about the Christmas long before, right? And then this is also curving because you are coming closer to the Christmas. So that was interesting. And then here we observe something like here, very strong yellow curve, because the end of the year was here. And essentially, in this end of the year, people, after the year passes, they don't talk about so much the past year, but they focus more on what we will do in the next year in all the tweets, right? So it's kind of like also a calendar effect of the year. Once it's passed, forgotten, now I start talking about the next things. And you see also visible here, because there's not much discussion in the first days of the January January. There's not much discussion of the distant past of this year, but there's much discussion on what will be in the current year a lot, compared to how would you analyze the colors here and here. So anyway, interesting analysis, we think, and very novel at that time. Of course, if you tweak more, do more deeper analysis, consider this before, after, proper normalization, because ours was just rule-based, very simple. You could have a better picture. We just show the direction. And we also later did another study of locations, not just time, but locations. So going over each day, we detected how far people in a location distance talk about. Are they talking about Starbucks in a near village, or Chicago, a couple of thousand kilometers farther, or about a nearby city? And we also did such a mapping. And that was also kind of logarithmic and quite interesting. On Thanksgiving Day, it was a very particular line that people talk about so many different places, referring to their friends or their travel relatives and travel to, and so on. And that kind of mass visualization could be useful. But now let me talk, or maybe let me check the time, 11:20. So I think it's a good time to have a break before another part, or, I'm talking about the event. So let's have 11:35, 15 minutes break.
Break, sir.
Yeah, now it's a break.
15-minute break.
15 minutes.
Yeah.
Okay, good. So break. Yeah, let's see what things.
You can work outside, sir.
Yeah, I will. Very soon I will go. Why today is a bit less students?
Yes.
Exams or something?
No, some exams are also going, and some are students, some are in these letters.
Oh, okay.
Yes.
Okay. Right.
Because I have also duty in second half. From 2:30 to 5:30.
Yeah.
Trái A gọi là trái không đúng. Trái
Oh, hello. All good, all good.
Also, ma'am will be teaching today for like from 3 to 4.
Okay, here.
Yeah, 3 to 4, and we'll go, sir, to her cabin, and those students that miss presentation that they will give.
Nice. What, after lunch?
Yeah, after lunch.
When is the last moment they need, because I'm going for 3 hours today.
Okay, you are going for 3 hours today.
Yeah. When
Then
is-
tomorrow 2 hours. only.
Yeah, but when is the last moment? They need
At 1:30 you can leave them. I mean, that would be sufficient.
Because I want to give them chance to eat.
Yeah, 1:30, around 1:30.
So 2 hours more. Yeah.
That would be completed, right? When you 3 hours.
There we go. Okay, that should be the time. Okay, still some people are missing, so let's wait a bit more.
Can I call them?
Yeah.
The end of session, please give us some pointers related to near real time communication. Like we are working to command and control. They have the commands given. They need to be executed within 15 minutes, 20 minutes.
Yeah, yeah.
If there are some research areas, research papers which are working in very short loop, like sequencing of commands in time.
Okay,
Of language.
okay, okay.
So that sense.
I hope I will have some good pointers for that.
That would be great.
But let's see, maybe you can explain
Okay.
later what exactly.
Yes.
Yeah, I think today we can do that. Maybe after, are you going for a lunch immediately? No? Okay. So we can have a short chat after we finish. Yeah, that's better. Okay, so let's start. Well, continue, not start. So I talk about extracting temporal information, about, temporal expressions, about normalizing them, evaluating, as you have seen. What is still left, and we didn't explain, is extracting events. So, of course, event is very, very temporal construct, but is not a temporal expression as we have. But often these events would be very useful to know for whatever reasons on the timeline, if you want to show something and so on. And it's could be supplemented by extraction of temporal expression like this Thursday here, for example, but it's still something different, or Friday. So as you say here, as you see here, we indicate by blue all events in this text. Some of them are more reporting previously happened event like said or citing. Nevertheless, they are also mentioned here. And you see that not always an event is a verb like increased. Sometimes it could be the move, which is a noun, right? Or the increase. This is what we would like to have, but this is actually still similar to name entity recognition tasks. So you can label a data set with those kind of spans and train bird or whatever method you want, or even ask LLM perhaps. Let's see how it would perform. I'm not aware of any study, but might have been already some to see how well they can extract information on events and perhaps even group them or put them on a timeline. Or timeline discussion we'll cover today a little bit, so there will be more on that. But this is a special case of information extraction, because so far we talk about relations, extracting relation like born at, married to, but these relations are often static. Being married, it takes a long time. Born to is also one event. But here, any type of events, and they could be repeating, intricately combined together. So it's slightly different type of relations if we consider event as a relation. And here, what I think is very important to know, and this will come up in many different temporal information processing studies, is ordering of events. And this is a well-known proposal by Allen, so-called Allen temporal relations, where you have two events and I think 7 at least relations that these two events can be positioned one to another. One can be before, they can meet, so the end of A is meeting beginning of B. They can be equal, they can have some overlap, they can start at the same time, but we don't care when they finish, or they finish at the same time, or it could be during. And you can't have more than that if you have only a pair of events. Of course, if you care about order, that B now is during A, then you can have a mirror-like reflection of those. But this very initial basic relationships between, well, events or or intervals in a more generic way are already specified and are limited. And often we use these relations, Allen temporal relations, for whatever we do with temporal logic and temporal reasoning and so on. So it's just a very basic information. And now I want to talk about another NLP task, which we actually proposed in our laboratory a long time ago, which is called document focus time estimation. And that is very close to temporal tagging and temporal information extraction. So if you have a document like this, you can run temporal tagger, perhaps idle time. You can extract and normalize, extract temporal expressions and normalize them. Like this is a duration. It has some code value, like every 8 months, periodical 8 months, right? You can do here 2007 normalization is obvious. It's just 2007. And the next year would be, of course, more tricky, but you can do that. However, some documents don't have many such temporal expressions. So document that lacks an temporal expression cannot be handled by temporal tagger, obviously, that's a limitation. And also temporal expressions can be weakly related to documents theme. Maybe this 2007 is not really so much strongly related to entire document's essence, the key aspect. But if you just run temporal tagger, you will use all of them in the same way, and perhaps we can do better to distinguish which temporal expressions are important, which are not, and if there are none of them, then do still something in the presence, well, in the case of a lacking temporal expressions. And also temporal taggers are not perfect, so we can improve it. So basically, we propose the task what to do when you have no temporal expressions or you don't explicitly focus on them and you still want to estimate temporality of a document. And here is one example. This document, whatever it is, it's actually something about US history and Poland information, and here is Nazi Soviet. No date mentioned at all, no time, yet we still can position it on the timeline with our knowledge. We knowing that Obama, that's something here, 2008, Independence Day, well, that's one day, disregarding that he was, I think, twice, if I recall well. But yeah, simplifying the World Wide Web, sorry, not World Wide Web, World Wide War, we can map the first one, Bolshevik Revolution also, and so on and so on, and can produce such a timeline for a document. So this task we proposed as an extension of temporal tagging, which operates on clear temporal expressions, but you see they are not present here. And yet we can still do something about time. So document focus time, T, if it contains basically refers to T. There is some relation to so-called temponyms in natural language processing that are named events or facts with clear temporal scope, just like we would have here temponym Bolshevik Revolution or Worldwide One. But Hitler here or Soviet, well, Soviet maybe not, but Stalin, Hitler are not temponym. They are just not event, they're just persons, but we know where they lived, and they somehow give information to generating such a timeline. Temponym tagging, okay, there are some solutions, but not fully what we want to do. we want to do more. So I will now discuss how we can estimate this document focus time. And this is old solution from 2013, but it's quite informative. So we will walk over this. Later, you can, of course, employ new, large language models, and we'll also see how they perform on a similar task. But now let's see how this can be performed, because it has many applications. For example, not only for text understanding, but also for information retrieval. Like you can say, retrieve me any news article or any document about this period or about that period, right? And then if you only rely on temporal expressions, you will not be able to retrieve such a document. But here we are able after mapping. So in an offline stage, each document could be mapped to this time period, and then online, during online search, query could be mapped, and then to the timeline as well, and we can find overlapping documents with the query. But how we can do it? So what we relied is building this kind of word-to-word association graph, and then from this graph generating possible times that will later mapped to, well, some kind of lines that can map to the timeline. I will walk over each stage one by one. So if we have a target document, let's say some words we highlight here as labels, character labels, doesn't really matter, but non-date, what we utilize is anyway large collection of articles that have these days before, and news articles in particular, and then we generate target documents focus time by this. And what we extract from those large collection, we're talking about millions of news articles, are each word, how is it co-occurring with what another word? So how often we find war and Nazi, sometimes because there were many wars without Nazi, Yalta, Hiroshima, and all these associations where the strength of association means how many times two words co-occur in a sentence, in a large corpus, right? So 1939 often co-occurs with Germany because Germany started a war at the time, obviously, and so on and so on. And you can already see that this simple handling every token and recording how often tokens co-occur could be useful if we consider that some tokens are dates, and that's what we want to distinguish as a special citizen in our graph, word co-occurrence graph, because later we can see how information from those dates propagates to other words. So we say that word W is strongly associated with a year. If it frequently co-occurs with this year, that's fine. Hiroshima probably would co-occur strongly with 1945 when atomic bomb was dropped on it. Also war, but perhaps less because war was also in other years. You have these associations between any token and a token that is a date, extracted from a large corpus of news. Could be just recent news because they always anyway refer to the past. But that's not only what we could do. We could look into second level term year association so that a word W is strongly associated with a particular year if many words that frequently co-occur with W are also strongly associated with this year, right? We can go a second level, one step farther, but we don't do it on a third level, fourth level, because there will be too much diluted situation. So we kind of decided only get about two levels. And here, association of a given word to a given year is done by looking at all the words, well, actually all the vocabulary you have, and looking how these all other words associate with our target word I, perhaps giving a square here, considering strong cases especially highly, and then considering a direct association of each word that is associated with a year. So basically it's a second level term to year association you can build. And this means actually you are propagating as if you would be propagating signals from the years. And of course, depending on how strong are these associations, the directly connected words will have stronger association, and those even 2 ways farther, like Israel, would still be highlighted, of course, depending how often they occur with words that already have strong associations, right? So it's a very simple solution. At that time, well, we used often the graphs, word graphs, and not so much neural network. And then we can extrapolate from a word to the level of a document. We can say that if a document contains many words strongly associated with a year, the document itself is strongly associated. So if we have, let's say, a document and it has the terms, and we know that each of the terms have certain association strength to the years, and we can even plot it, we see that word B and C are twice appearing in a document. So we generate a kind of time series that is a summation of the individual words time series with the weight indicating how many times these words appear. So the final focus time, or focus time curve would be like this for this simple document. And however, we observe that for some words like man and city, they are so non-specific that they have stable associations with years. And maybe we should treat them separately than perhaps very specific words like Nazi, Hiroshima, and so on. So we propose to incorporate something called temporal entropy, so variability of a word association over time, which is also shown here. You see that B is more uniform over time in its association, which is computed from the equation we applied before, as opposed to word A. And where A, we reason is more useful for us to if it appears in a document, we should give more influence to the A word than B, because it is less uniformly associated with years over time. But not only that, we also consider kurtosis, and you may not know kurtosis, but it's a statistics of a plot, distribution plot often. If it says that if there is one strong peak for a distribution and everything is flat, then kurtosis is much higher than case of many peaks, right? So we again give a preference to words that have one individual peak, as opposed to case of entropy where actually you could have many peaks, because like Hiroshima case was especially very good. It was so strongly related with 1 year only. So we'll also look into those to play down the role of something like war and earthquake, but increase the role of Hitler, Stalingrad, for example, because they have stronger kurtosis, and anyway, they have probably stronger entropy as well. And we use them as weights, right? So we take the document, we take our knowledge, word coherence graph, and then we all do these steps: temporal entropy, temporal kurtosis, association of terms to temporal signals, so the dates. But not only that, we also try to pick up how words indicate the meaning of entire document, and that is irrespectively from the time signals. So which of the words here you would say are crucial for capturing the essence of a document? And we apply so-called text rank, which is also operating on the word coherence graph, but it's like PageRank. I'm not sure you heard about PageRank algorithm, right? It's the way that Google, around 2006, sort of organized the web, because there was a lot of spam at that time. So a document is more important if it's linked by many important documents, right? Essentially, it's a propagation of importance signal in a web-to-web linkage graph. Here we have term-to-term coherence graph, but idea is same. The word is important if it's strongly connected to other important words, and then you can do essentially Markovian walk on the graph and calculate node scores. A text rank doesn't have direction like you would have on the web, that something links something, but not vice versa. Here's just the two words cohere, but anyway, you can still benefit from this. And then these words which have high score with a certain threshold we apply would be considered as representing essence of a document. What we do with these scores, we use them again for serving as a weight for a term, how term is important for a document. And we have also other terms like how word is associated with each year, what is the also kurtosis, what is the entropy of each word. So all this together, we actually consider these weights, temporal weights, semantic weights, as in a previous slide, and drove the curve for a document. We're aggregating each word, and then we need some threshold, which is another story how to determine in the simplest way, just experimentally in a more tricky way. You could try to define it in a data-driven way. Anyway, anything above the threshold could be considered as a focus time of a document. But it's interval-based. If you just want maybe one only year, you can reason on the peaks and take the highest point and just say that's my focus time of a document, even though it could be, you know, in an interval way longer, but you just want 1 year, depending on application, what you want. But that's basically the essence here. And another point here to mention is that we might still have temporal expressions in the document, right? So not always is purely text like we have seen so far. There could be temporal expressions. So let's also use them, mapping them to the years. And then together you can combine everything, right? And if you have these dates, how to process them. So you can use Gaussian kernel density estimate actually as if you would sum all these temporal distributions, normal temporal distributions. Each one is positioned on a year that was mentioned here. And we need some parameter of how it spreads, but a standard way can calculate. And then you have some, by summing all those distributions, have a estimate of density. And this is just considering these existing temporal expressions. But as we discussed, we also have the component that uses any word and also maps them into the kind of curve like we have considered before, the red one curve here. And then you can combine those two. And so to evaluate this approach, we use some news article data sets to first of all build a graph. And there were many news articles for different countries because we did it on the country. So anything about France, French news articles, Germany, and so on. And then we have some test collection, test data sets. So Wikipedia page where we know this snapshot is about this event in this year. The textbook of a history, we also know from, let's say, a title of a section, which period this section is about. From the web, you can take news articles and also easily label to some kind of section. And we employed different measures. One measure is the average error. So let's say the ground truth is like this, but we estimate focus time like this. In a simpler way, we could consider the closest point to the actual ground truth. I mean, not the closest point, our decision to the actual closest ground truth as an error is instance-based representation. But if you have interval-based representation, you can take ground truth, you can take estimated time, divide everything to some unit, and then see what is the overlap, right? Here there is no overlap, there is overlap. Oh, why this is plus? I think it should be minus here. Yeah, sorry for that, but basically also here, something is wrong with this annotation, but the overlap should be whenever, I mean plus whenever we have agreement. And then we can calculate some correlation measure based on that, which will tell you from -1 to 1, what's the things here. Oh, okay, because, yeah, but yeah, sorry. This plus means basically you code all these indicators, and this blue plus, blue minus is you code the indicators. And now you compare plus to minus, plus to plus, minus to minus, right? So it's actually correct. And then we calculated, well, it was a long time ago, so we didn't have very good baselines, like just dates considering a randomly baseline and LDA baseline. And we had a much better case in terms of error, smaller error on different data sets, considering also the Wikipedia, and also the correlation was higher for this case, considering many baselines. But well, it was done a long time ago, but later a good number of papers picked up this task and they employed some neural network solutions and so on to do this time focus time estimation. We also studied in these experiments, can you estimate focus time well for recent things, and how about very old ones? And then, well, there is less historical information, so then you have less content in this word coherence graph. The error was larger on different data sets when you care about more distant focus times. And we also did later on more extensions to it, but in a simpler way, using n-gram information to date this document. So this is more about dating of a document, actually, not focus time. When it was written, we could use all these time series from n-gram data set over books. I think I mentioned on that, and aggregating a frequency of individual n-gram, 3 gram in this case, over time, and summing it all together, and then finding some creation date of a document. It's slightly different concept from focus time, but it's based on the type of language you use, the type of words you use. If it's computer, you know it's not will be the time of Shakespeare and so on. If Einstein is mentioned, that it has to be after he was mentioned. You can still do this, and we generated some system that is operating also, still operational. You can copy and paste from anywhere, any text. This is a Sherlock Holmes document, and generate this kind of plots, see based on different n-grams what's the most common date, have some evidence which says supporting 1907 are these 3 grams, observing machine that perhaps it was common at that time in a large corpus of documents, and reason on that when the document was created. But it's very statistical, it's pure and fast, and you can estimate the age. We went farther with this solution in the sense that now we made a heat map, which words are old and which words are new in a document. So Sherlock Holmes is a new term, but was not that he, this kind of program, I think, was quite old, recorded in US. So you can see what are the recent terms, what are or recent n-grams if we operate on n-gram, and what are the old ones. Some of them are not reported, like this Adler or D written with capital characters or eclipses, just not enough data in our training corpus. So it was not labeled. But we could also reason if a text is using many old terms or new terms, zoom on every term and have a frequency plot over time. Then also how the words changed the meaning actually over time, like dubious a long time ago might have different meaning, and cold also. Cold now does not mean temperature, but someone is cold to you, so it acquired a new meaning, and that's why it's indicated here. This was also possible to study. We have a solution by comparing the vector of soft in this decade with another decade and seeing some kind of similarity. Well, and so on and so on. What I also want to show you, it's another age estimation problem, but on a type of document, which is of course web, as you can see here, a web page. So we were thinking like many web pages don't have indication how old is content on there. It could be written in the news. Okay, you might have some date here, but maybe in this case, you not necessarily have, well, here is May, but anything, this image, you don't know when it was put on the page. Some other information may be missing, anything, right? But we want to get some approximation. How old is this image? Is this person here perhaps, photographed 10 years ago or so? Is this news actually already obsolete? Not always you have a date. So we generated a system, we developed a system that adds these frames for every element of HTML with a small date in the corner. And it was a very old study, it was 2007. No one was thinking about dating web documents, the components of web documents at that time. What we did is we utilized Web Archive, searching for each component. When was the first time in the sequence of snapshots of the page it was recorded, right? And then if you have a couple of different objects, You can do multi-binary search. It's a binary search, so it's faster than just sequentially searching. It's not that important. But we utilize something called Web Archive. I don't know if you utilize Web Archive, anyone had anything to do, but it's useful seeing if data is missing on the web, but you know it was at some point. And now it's more and more utilized, not just for studying history, but also for legal cases. A company may have posted something on the web, which might have, for example, wrongly directed some customer, right? And then the customer acted on it, and then later company remove it. You know, a couple of years later, the judge wants to know, was it really there or not? Internet Archive, one of the biggest web archives, can you provide you a legally, valid evidence that it was at that time and this time when we crawled the page, this information was there. For whatever reasons, for journalists, for legal professionals, for risk management, you can imagine a myriad of applications that this history, how things were reported on the web matters. And Internet Archive is the biggest organization doing that. We often have in Europe some country-specific archives, like Austrian Web Archive, Icelandic Web Archive, where the National Library is charged to capture everything that is in the domain of a given country, Icelandic domain or Austrian. Typically, smaller countries do it because they can manage to capture a web of the country with the domain, let's say .at, that would indicate just Austria. You can also do it per language, .jp for Japan, but also anything that is in Japanese, right? You store and preserve. But Internet Archive is operating in US. It was founded by Brewster Kahle, one of the successful startup owners in US at that time. And he decided that, well, it is like a library where you are storing something important for society. And even more ephemeral, even more changing it is. Why not to preserve it? And he donated $1 million for that and started it as a non-profit organization. Later it became bigger and bigger, and maybe it's even bringing some resources. I don't know, for sure many donations, because it's the largest scale project of this type. You have this Wayback Machine where you can type any URL, your company perhaps, your institution, and see how it looked like in the past. Quite informative travel in time possibility. These numbers are a bit old. I'm sure there's many more now. It takes a snapshot of the web every 2 months, and it's not crawling itself. It's relying on some providers, some search engines that is sending entire dump to them. They also have in Alexandria, why Alexandria? Because there was a famous library of Alexandria in Egypt. They have a backup snapshot of entire data. It's so precious that it will somehow disappear for whatever reason, flood or earthquake or so. It will be too big a loss for the humanity. So they decided to mirror entire data in Egypt. How they shifted the data to Egypt is interesting. They decided it would be faster through the ship, actually, with many hard drives, than sending through the web because of this amount of data. Anyway, what you can see there, for example, I Googled Yahoo, and this is the very first page captured of Yahoo. It's maybe Yahoo is not that common these days. I should choose a better example, but this is a yesterday's, no, not yesterday's, but a couple of days ago, Yahoo. You see what is similar. This advertisement was not displayed correctly. I don't know, for whatever reason, but you have the logo perhaps in the same style, but you don't have what was before, all this dictionary. It was like a hub at that time. Yahoo was acting, serving, pointing to some list of pages curated. Obviously, we don't have it now. We have a search engine here that is powered, if I recall, by Google. I'm not sure. I guess by Google search engine. And then all the news and advertisement and shopping, so it became something bigger. Well, you had also a search here, but very limited at that time. Anyway, if you are interested about any URL, you type it to Wayback Machine, and you typically get a list on each year, how many snapshots are there. Indicator here was mentioning, is the content different or not from the previous one? So you have all these links. You can do it also. It's a more recent calendar view. They show, aggregate per year and in a given day. because collecting this data, it is, of course, time-consuming. Only major websites, this is Kyoto University where I was before, they had like 700 times collected from the very early time to, I think, the time when I created this slide, 2013. And the good point is that they provide a nice linking style to all those snapshots, right? You indicate the server, you indicate the date. This is a time, I mean, date, time, all the detail up to even seconds if you want, or up to minutes, and what is this resource. And of course, if this date is not available, then the nearest one is returned, right? So you may make an error here, but you will get the nearest snapshot. Obviously, the problem here is that you have fixed representation, fragmentary, I should say, representation of a data over time, even if you not only use Internet Archive, but use something like Austrian Archive, all the, set of different archives. Even search engine caches, somehow you get it, I don't know, maybe in the past it was possible to get through API, now not sure. But if you collect it all, you will only have some fragments. You can reason what was here between, but it's lost essentially. I gave to one of the bachelor student a master thesis, master thesis topic to try to say something what could have been there. Given that you have only those snapshots, if they are identical, the problem is simple. But if they are not identical, like this color, then at least try to guess how many changes were there, or what was this, change positioned, or perhaps you can even try to guess what was the content, considering there could be other similar pages, and there's also some links between pages at that time. It's a complex project, kind of archaeology, right, of the web. We will never be able to say exactly what was there, but we can say how much changed, how often, at what time, and perhaps some kind of topics, considering whatever we have here, how was periodicity of this page, and what are similar pages, and so on. Anyway, we have this missing content, but as you say, we utilize it, because that's why I started this talk, to date different components here, considering this archival data. And I remember Adobe company, they released also very nice extension in a similar vein, that you could, and there is a whole demo, that you could focus on any page and you have a timeline, and then for a given component, let's say only this first news, you can go over and it will, like a timeline, will show you, different content that was there. They even had nice example of a map of streets with a traffic intensity, and then you could go over every Friday, let's say, because today is Friday or something, and see it was common or not, extracting from Web Archive. But the best solution was for price tagging. So Amazon, and you go on this page of a product and see if it was somehow changing the price before, maybe it's constantly increasing or decreasing, giving you a context what you should do later. Act now, buy, or wait perhaps, or whatever, right? So, and that kind of solutions was also proposed. And here, in addition, we also designed some kind of visualization, how the page changes over time. And it was BBC page, I think, couple of years. And just here are top terms extracted from each segment, each year, overall top terms. And this is increasing the more changes you have in a content. So here is less dramatically increasing, here is more. It was very early. It was, I think, 2008, where we tried to visualize a very first way of visualizing history of pages. There might be some application these days. Web has now longer history, I would say. I can feel we need more solutions, because currently it's just Internet Archive, its own interface, but you could potentially consider doing with it more than what is available now. It's kind of a niche topic, but I would say very important. Especially as now historians even move to Web Archive. They study Web Archive, do not study things like, because it's already quite long history than just text. Now I want to tell you a more recent way of focus time estimation that I did with my PhD student that was published in CIR 2021. We focus on a more challenging case where you don't have entire document, but you have just a short span of text, like this one, for example. There is often a description of some event. You need to have a model to estimate this occurrence time of this event, but essentially it means focus time, given some data set, right? As your knowledge base. So the setup is like this: event description, a short one, the granularity, do you want per month, per day, per year, the supportive news collection. We don't imagine anything structure here, just a news collection, and then find occurrence date of it. So quite challenging given how short this is. Like this one, right? And then your answer per monthly granularity and using this data set perhaps should be this, right? This is what we want, this answer given all these inputs. And here is a data set we used, right? You see how short it is. Even someone quite versatile in history but non-professional might be difficult. And this is a time, the ground truth time for these things. And here you see that we also had a lot of content not in Wikipedia, so quite challenging, or partially in Wikipedia that perhaps only year is there. And we wanted, well, one way of using it would be already automatically suggesting temporal information for Wikipedia if someone has such a wish to contribute to Wikipedia. So how we solve it, right? So we use transformer with different stacks of encoders and convolutional layer here to aggregate from a time series a lot of information into one more combined information. And then we have a softmax, so probabilities over different years or months, depending on the granularity or days. And we considered New York Times data set, which is spanning 20 years, but it has about 2 million articles and is indexed. And as our test set, we have 22,000 descriptions of events. They were collected from Wikipedia year pages and spanning time like here. Let me see if I have examples. So this is Wikipedia year page. Any year you type here as the name of the page, basically an address like here, you have all the major events. So we collected this, of course, masking all the temporal information, and just given this short span, the task was to predict this. We assume this is good one as curated by many people. But of course, someone might argue Wikipedia is collectively done, but still. And the solution that we did, given, let's say, input event and given underlying news collection, was to generate 4 times of time series for this event description. One is just top n number of relevant documents. So as I said, we have retrieval here, right? Where it was, I mentioned, data was indexed. Yeah, I think it was in the case of it. Not this one, so for scrolling. Yeah, Elasticsearch. So we had retrieval by BM25. So you retrieve documents considering this description of event as a query, very simple, and you consider top 100, and then you look at the timestamps of these top 100 documents to generate first time series of publication date of relevant documents. N is 100 here, but could be defined. Then you consider in this document, what are the mentioned dates? So you have now not publication by, but this kind of temporal expression based time series. You can draw another time series. Then you calculate what's the similarity between your short event description and every such a document or every sentence containing time expression. You generate lots of time series, 4 of them, which are here as an input. That's why the name is multivariate time series. And then the text is not included anymore. It's just all this time series only, but they are processed by convolutional layers, by transformer, And of course, they are trained on many instances where we have, I forgot how many, but we have 80% of these 22,000 are used for training, and then development and the testing 10%. So let's see what we achieved. We had many baselines here, you see, and the step CNN and step transformer CNN, we didn't use transformer, we just used CNN layer, was giving this value. This is accuracy per day granularity, so super challenging task because how many days you have in 20 years? I don't know, but a couple of thousand. So randomly guessing, it is a random guess, gives you just this, accuracy. Then I think, what is this? CNN, LSTM, and then neural language model. I would need to check what were theirs, but they are in a paper. I think there were some competing also papers because they are cited here. But you see that they didn't have that good accuracy per day as our. Here is mean average error reported. And this also happens for a year. If you just care about year, we have much better accuracy and smaller error. And if you remove those different time series, we have 4 of them, you see that accuracy is dropping. So actually, all 4 of them using is giving the best result, right? That is also established here. And then what we also found that if you vary this number of results considered, I said actually n was 100, but now you take only 20 out of 100 or only 30 and see how much you have accuracy. This is the result. So if you have just one document, you don't get good result. You need a bit more. This is our approach, but you have saturation. So you may only care about, let's say, 20, top 20, and you don't care about more. But the baselines are now suffering from increase in the data because the more noise is there, and they are not so resilient to noise. And our approach is more stable, even though you put more and more documents, then of course it's a passing mentions, not big relevance to this event that you input, and so on, right? And then we studied what's the effect of the length of event. If you have many words, you get better accuracy of dating. That is obvious. They have more information, and also this study. And let me check on the timeline if we need. I mean, tell me if you feel like you want to have a break or we can continue. I don't see any urgent. So let's now move for a very brief time to ImageWord, just to have a bit of a refresher. And then we come back later to text analysis. Anyway, this is about, because the whole stack of slides I'm now showing from the morning is about time stamping, dating, and focus time estimation. So all this representation of time of a text, but now I also want to show you images. You have many old images in libraries, museum, archives, on the web, and so on. Sometimes they have a date, sometimes not, and then you need to have a tool to estimate it. Or sometimes in some museums, you are not certain what is the date, right? We may verify it. And then you can build a search functionalities like find me all Vienna images from this year, whatever, right? And by the way, can you guess what is the age of these images? How old would be the first one? What do you think? Anyone has a guess? The second and the third. What would be the first one? What do you think? 1940s, 30s, 50s, right? The second one, at least decade. What would you say? 80s. And the third one? 70s, right? The actual dates are like this. So I think you were right, but here maybe someone has a good camera, even though it's a long time ago, a richer guy, and did in a color and with a good resolution. But this one is actually 89, because if you look more closely, you have more recent cars on the backside, right? So this adds the challenge here. Right? Anyway, what we want to do is a tool that will generate such year for an input image, right? And then the solutions we employed, the first solution was building a classifier per each year, but a classifier that was based on an order. So the question was like, given this image, tell me, was it before or after? Sorry, no, first after 1930, was it after 1931, was it after 1932? All of them with all the scores, because you have many classifiers essentially for this. And you can do reverse, was it before this year, and again have a set of scores. And then what we did, because you can have discrepancies between these classifiers, right? This one says after 1930, but this one says no, not after 1931, right? It will be strange because they are ordered and it should be, you know, like this only, never increasing, let's say. So we provided essentially a fully connected layer and combine all these classifiers together. So they have to agree. A little bit of the trick. It's so-called rank consistency idea, what we took from another solution that was not based on dating images, but estimating the age of a person by looking at the face. The idea is still not that far away. Age estimation of a human versus age estimation of an image. But by this kind of imposing order on these classifiers, we could have better results. So this is case of consistency, this is case of non-consistency. So that was the first approach. The second approach was based on detecting objects, like here, the dog, the bicycle, the car, and then having individual models to date each of these objects, and then ensembling them, aggregating the decisions. So for the second one, we had data set of 1 million images available. You can download them. I can give you a link later or find them on my papers. Images like this with their dates, right? And then we apply, at that time, there was 2020, I think, a couple of years ago, we applied the Tektron model to detect objects with their sureness level, like here. And then we applied classifier per date using ResNet 50. It was well known image processing application. So you can see that the person extracted bounding boxes are those, and then we had a model trained only on persons using ResNet 50. Because a person given in the image has the same timestamp as the image, so it was very easy to associate label. We only have these 6, I think. No, we had more objects types, but we only care about those 6 because we have large number of data. And then the tool, the Tektron tool at that time could only do this fixed number of objects. I don't know why tie is there. Tie was detected, different types of tie, but okay. And then the image distribution in our data set was a bit challenging. You didn't have much data initially, and then vast amount of photos. Well, after certain day when which popularized perhaps the cameras. How these images were collected at 1 million, we didn't collecting ourselves, but they were picked up from Flickr. You know, the Flickr is an image repository in a very simple way, actually. So whenever an image has a tag, which was a date here, they grab it and they consider the date as the year of creation of this image. You can imagine many ways it is not true, but most of the time it will be working. And maybe they did some, because it's a paper that did it, maybe they did some sort of later filtering, but the main idea was that. A vast number, quickly, dirty, but data is there. And here you see our solutions, how they are performing in terms of mean average error and root square mean square error. The two are often used whenever you have some sort of a distance-based decisions. The first one is most generic. The second one is typically introduced to penalize big mistakes, right? You square those, and the system has to be more penalized for overshooting or undershooting. And you see that The first approach was giving something like 6 or close to 7 error. Coral, which is the rank consistency approach we borrowed, reverse Coral, employed to classification, employed to regression, baseline, and so on. But the second approach, the object-based, was the best. Roughly 6 years, 6.5 years on about how many 70 or 60 years long span of a data. Here you have a grand Troussier, extracted objects, and dated based on the language model. Sorry, not language model, person model, which was trained only on persons. And we already observed a problem here. One problem, as you can already guess, is that the object that was bigger, because closer to the camera, having better precision resolution, was considered by the model as more recent, like this guy, as opposed to lady in far away. We were not from an image processing field. We believe this is sort of maybe well known, at least something to reason for later, to counteract those depth issues. And here we also could analyze where the model is really looking at by the attention. And I think it is, giving you some explainability. Are you sure you will look into person or the car or so on and so on? Okay, so this is actually the last slide I have for the first slide deck. So I think it's a good time to take a break. And so now it's 12:30. Let's do it until 12:45. The remaining, we will have only 45 minutes, which we will cover with a summarization, a discussion. So 15 minutes break. Let's have now.
The second half, man will take 1 hour.
हाँ घूमने गया था। वहाँ था सिर्फ बहुत गया अभी इतना घुमा और घर से गया यहाँ एक बार घुमा हाँ सर सब पुराना हो गया ठीक है बोले क्या था हाँ एक बार तन हुआ सर लेंथ ही बना देते हाँ ये तो बिल्कुल करना हाँ हाँ एक हाँ 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 वो एक कराए थे ना हाँ सर्विसिंग कराए थे ना वो करने थोड़ा हो जाए हाँ हाँ नहीं, उसमें तो बोले सर्विसिंग में जो पैसा, उसमें पैसा नहीं था इसका इक्विपमेंट हो। ठीक है। वो सर महंगा पड़ेगा, 30,000 के आसपास लैब पूछता। सर आप समझ रहे हैं, ये प्रोजेक्टर होगा कितना, 70,000 80,000 का होगा। हाँ। नहीं, लैंप पड़ाता है अंदर में सर। ये तो लेंस है सर, सामने जो दिखता है ना वो लेंस। और सिर्फ लैंप चार्ज करना पड़ेगा। दोनों अलग अलग मॉडल है। हाँ। नहीं, कंपनी सेम ही है लेकिन मॉडल अलग है। ये सर वो सर आपको लगता है कंज्यूमेबल में नहीं होगा होगा वो रिसीवर्स। हाँ, माइक वाला रिसीवर्स। हाँ, इक्विपमेंट में सही से। हाँ।
Okay, so it's good time to start. I will talk now about temporal summarization. So just to start with, background summarization is a task that everybody knows. It's shortening some text or a couple of texts. And automatic summarization would do it automatically for us. You can ask to summarize into very small, just one gist of a long document, or you can make a bit longer summary. It's a very much time effective format of data because you don't have to spend much time to read it. So we need it, especially now when information is so much coming in a large quantities and often. And we distinguish summarization based on single input or multiple input. Typically multiple here means related documents that you summarize. And then based on the type of summarization, or one might say output, I already mentioned that before, extractive versus abstractive. So extract sentences from document or documents, or everything abstract, write in your own way, clearly from the scratch. And news articles, that's what we'll focus on when it comes to summarization now on, are very commonly used documents online. Actually, one of the most common consumed types of online documents. So I think doing here anything that helps users to read it in a better way, it's very important, especially as we have complex landscape of news changing very quickly, and we often need this helicopter view, and we may be lacking some contextual knowledge when we read some articles. Of course, journalists try to do their best and give us some kind of background often, but it may still require some knowledge, and not always is perfect. So the temporal summarization would be a summarization where you care about the time a lot and incorporate it as one of the main features or as the feature defining outcome, not the input feature. And we will discuss today those different variants of temporal summarization: timeline summarization, the most well-known task; extension, multi-timeline summarization; then a bit more specific tasks to consider a special type of documents, timeline document, comparative summarization, and then even, which I found the most interesting, future timeline summarization, but that will be about it soon, and the most recent research. So in a general overview, timeline summarization would mean you have a bunch of texts and you create, let's say, a timeline of most important things, like this one here. This could be for a certain game, I think tennis game. So that means that the times are very fine-grained, but it could be a days and typically is, or even a years when you make a long summary. And these are examples of the produced timeline summaries from a literature, from ACL 2020. There was a survey paper on that, news timeline summarization, and you see how it looks like basically, right? So the query here probably was Enron company, and then major events as collected from a large corpus of Enron-related news are shown here, and also here, basically a very short summary for each relevant date, and not always every day is considered here, right? Because nothing happened perhaps in between, so it's not listed. And we have these kind of timelines on the news and in Wikipedia. Wikipedia is here, for example, as we discussed already, quite prevalent. Or we need to generate those. I think this one is, yeah, this is based on months. So May and then June and you know, a bit longer summary here. What is typically done for timeline summarization is the unsupervised approach, for the reason that we don't have so much training data for this problem. And it usually demands a lot of data as an input. You need to input maybe 1,000 news articles and then one summary. And then how many summaries with corresponding 1,000 news articles sets you might have? Not that many. So I will talk about it, how to make a data set. But it's often done in unsupervised fashion by clustering, by picking up sentences or generating sentences and then scoring them and selecting. Just like here, news article corpus, the query might be there, so you may constrain everything to, well, one topic if you want, and generate such a news timeline. Well, yeah, timeline. So given a corpus D, generate a timeline T, which is nothing else but a sequence of timestamp and the sentences, or perhaps summaries if this is a bit longer. So it's a sequence, ordered sequence of summaries, each one with a timestamp. That is what you generate in a specific type of summarization. And I want to say, while typical text summarization problem has been rather solvable by using LLMs, this problem is not yet, because it's so much challenging. You have temporal aspect and you have typically many documents. It's not that well approached by LLMs, not so easy. At least, and a lack of training data is another issue. So here is one way to do it. You cluster the news together, perhaps centered around dates. Then you generate some intermediate representation. This could be some vector or some event mention extracted from those. You can score them and then create a summary based on scored snippets of text or perhaps embeddings, but you can come back to the previous sentences to pick up them for generating a summary after you do arrangement here in many ways. This is more abstractive, so I think it is more like some portions are scored and then they could be, yeah, sorry, but I forgot exactly how it was done. So maybe I will skip that one as for now. And just want to mention that we'll see later how to do it in more detail, but I want to mention that we might have a generic timeline summarization. We might have query-based timeline summarization where you need to extract from an initial data set query-relevant documents and then generate a timeline focused on this query, right? Let's say everything about India for the last couple of years from any news, right? For example, or anything about John Lennon from music-related news in England. And, anything can be input, and query could be also anything. And you can have comparative timeline summarization. Perhaps you have two data sets now. You might say, I have news articles by Republicans and news articles by Democrats. Not by, but let's say by the media that supports these two parties. And then the query might be one, let's say election or something, and you can generate timeline and contrast it later. So the way you generate this timeline here is affected what is in another corpus. So it's not like separately you have two timelines and then you just compare them. You generate them when one is interacting, one corpus interacting of documents with another. comparing and so on. And first I will start with evaluating LLMs on this TLS task. So this is just a repeating slide that we have and documents as an input and K summaries, but by this we mean K different dates where the certain event is picked up and discussed. And we might have actually two different styles of generating such timelines. One would be focusing on dates, the other would be focusing on events. For a date case, we first try to pick up representative important dates by just time-based clustering. So only considering the time point. Whenever in a certain date there is a lot of things going on, we can pick up this date and say this is something where I want a summary to put, and then later I create a summary from anything that was clustered around this date. On the other hand, for event-based approach, which I personally consider better, you extract first sentences from articles, you group them by events, clustering, and then associate each cluster to a certain mean date of sentences in this particular cluster. So two different approaches, and we don't have too many data sets for this task, unfortunately, but they are often used, at least, just because it's so difficult to generate them manually. However, more and more we use automatic solutions later on. You see the different topics are, at least in these top 3 data sets. Sometimes for a given topic, let's say presidential election in US, you might have actually a couple of timelines because they ask a couple of people to write a timeline on this. But the numbers of dates per topic and documents per topic are quite large. So it's hard to input into LLMs something like, you see, 2,300 news articles because you pay for a number of tokens so much. Then you use some technique, actually we will use, to summarize each of those articles before they are aggregated even, to decrease the scope of data. And how these data sets were done. So timeline 17 has 19 timeline summaries for 9 topics, and they were collected from large news providers. And then for a given summary there, the users were searching for news articles published also in CNN, BBC, NBC that are relevant to this summary. So you start with a ground truth summary that is there. It's quite maybe easy to find such a summary, and then you supplement data set with news that are somehow related to this summary by picking up a couple of queries, issuing them, maybe some filtering more, and so on, removing duplicates. This is done, and as you see, this is the collection you have and the summary that was generated are not really so much coupled. You first pick up the news summary, and then you supplement the collection, but it's not like you ask users to take these documents and summarize them, right? It would be different. We don't have such a good data set, unfortunately. But anyway, you see how many ground truths we have per each topic. So this is British petroleum oil leak that happened in US, something in Egypt. I think this is some disease outbreak, some problems in Haiti, Iraq war, and so on and so on. This is the very oldest data set. Another data set are crisis-related timeline summaries, a similar way of creating from news agencies and supplementing with articles with their dates and numbers here. So you see, you don't have actually many data instances, right? The number is 22 timelines. Previous one has 19. What can you do with this number? Not much when it comes to traditional supervised learning. Here, entities data set, another well-known, has a bit more, but still this is very little, 47. And I think it's a very similar way of making it. Pick up first a summary, supplement by news using Gordian API in this case. And this is not just events, as we have seen before, but focusing on some entities like a country or person or so. And this data set we actually created with my Portuguese friends is the largest so far, 178 topics and 100,000 of news articles. Also the first one multilingual. There was no in different language than English. And we basically focus on COVID, crawling every day major events related to COVID, and then crawling on the same day stories that had a COVID as I think, a keyword in a title, or yeah, maybe also in an abstract, don't remember that one, and collecting such data. So it's domain specific, but spanning many articles, long time period, relatively, and on every day you have news. So all the structures are shown here, all of them news, and the number of topics, it's not large, number of timelines also not large. Yeah, I think we have different topics here, so that's why the number of timelines is quite large, and so on. But let's suppose you generate summaries, whatever way you use to prompt LLMs to make such summaries, how to evaluate them, how to make sure that these are good summaries. As I already mentioned, a very simple way to calculate a reference to generated text is a Rouge. You basically see the overlap in terms of n-grams. Here one indicates unigrams, but you can have two that you could consider bigrams, like so the sliding window with size 2. But if you consider Rouge 1, you just see how many words are, let's say, in what the model generated, and overlap between what a reference text, which is gold summary, gold standard in our case, has. And then you normalize it in a certain way, so matching to the total number of n-grams or grams in this case in the reference text. But what to do with the timeline summary, where you have also dates, right? And where you have a text on every date. So the community proposed this evaluation way, which I think is quite reasonable. Let's say you have a ground truth timeline, summary on a certain day, and you have a system-generated timeline. The simplest way is concatenate all the summaries here and here, and then apply Rouge. Rouge 1, Rouge 2, Rouge N, and there is also Rouge based on longest subsequence matching, could be a bit more refined, but typically we use 1 and 2, and that's enough. But you see, you concatenate them, so you lose information about the time, you don't care about it. Here, on the other hand, you only calculate Rouge whenever there is agreement in days. Exactly the same day, the two summaries must be to calculate the Rouge score between them. If there is no corresponding date, like in a second instance, in the system or in the ground truth, you just have a score 0, right? So you have no matching at all. So it's very strict here in terms of time. And then here you compare only dates, whether the correlation perhaps or F-score of these days is same as here. And then you can have some more relaxed version of align Rouge. You allow for certain tolerance in terms of time, right? So maybe 2 days before, 2 days after, it's fine to compare. Well, this could be considered as a combination of this case here, well, with a bit more relaxation. So yeah, many ways to do it. This is just described here. And this is actually the work done with Sriparna Saha professor. We did it last year with one master student, I think. We examined these LLMs, how good they are at generating timelines for our data set, this crisis, timeline 17, but using baselines from the literature, right? So you have some scores on concatenation, agreement, align, and date. And we now wanted to see how language models perform as opposed to these baselines with different size of parameters, right? I'm not sure this 1.7 is just a guess probably. This is not reported well in my understanding, but anyway, it's the largest. And we had a problem with too big input of text data, simply. So the procedure here was to basically sort articles by publication dates, so nearby chunks of stories around the same day, and then concatenate it, and then summarize it, so grouping by date and summarizing, grouping by date and summarizing, and then such a processed input feeding again to LLM. Actually, LLM was used to summarize those things, feeding into LLM to ask to create summary. Otherwise, there was too much data. That's one way. We calculated the average number of groupings and so on. It's maybe not so important. And comparing these numbers here, let me come back, for a different data sets, different language models and the style of agreement, you would observe that, yeah, the numbers are competitive, especially if you use maybe Rouge 1 you consider, and this Flantify as small model is performing quite well, not too far away on the dates. So it's a reasonable approach, but the results are still very, very, leaving much room for improvement because you consider time, there's unsupervised way of doing it, and you have a lot of data and you can have disagreement in terms of semantics and the date. We also tested another approach using relation extraction to create a knowledge graph, some kind of structured representation of relations from the news, and then feed it to LLM to generate timeline summary. And then this one was, performing a bit worse, actually, if you compare to the baselines. So not that promising, but perhaps combination of both could be useful. Again, I can point you to particular paper, or you can easily Google it if you type timeline summarization LLMs and just last year paper. This is study.
So all fine-tuning based?
No, nothing was fine-tuned. No, everything is zero shot. Actually, also zero shot. You just input data, which is so long that you need to, so you can't have many examples input as well. I think we left it for the future. If someone wants to study how few shot would perform here, maybe this is something interesting. And here we also have some ranking time approach. So it kind of similar to the date-based approach, as I said first. So summarize dates. I will not go that much into detail here, but performance was also quite good. Anyway, very simple approaches without fine-tuning. And the problem was to systematically, step-by-step, decrease size of data, retaining key information, and then try to generate a summary from that. And it says that GPT-4 was having best performance, but also Flantify. But other models like Llama were not that good. And using basic approaches can achieve good results, but still room for improvement is there. Now I want to introduce a relevant task, which we call multiple timeline summarization, which we think is more realistic, because you can't assume that you have just one collection of data that is so well maintained that that's all what you need and that's everything and that's pure, clean, that you create a timeline, like everything about India or everything about COVID. You typically will have a mixture of data. And then you create actually multiple timelines. That's why we coined this name MTLS rather than TLS, where M would be multiple timelines. Perhaps if you have anything about Apple, all the news about Apple, or actually not even Apple, you can have just a simple query lookup for Apple in a sense, not only company, but also food you will have. So very dirty collection. And then you want to create a timeline, it would not make sense to put everything together, right? Even if I focus only on the company, you might still have interesting timelines that do product per delivered based timeline or CO or whatever, acquisitions of the company, name it, but you can have many variants. So that's what we think. But now the challenge is bigger because now you need to, first of all, find how many timelines you will have from a certain noisy large collection, and then each one of them you need to create, right? So input is a collection of timestamp articles, but output is a set of timeline, large T, one timeline, where each of them is timeline like we have seen so far, so a set of summaries in a certain days. And how to create it? It was the NLP conference we published with one master student in 2021 when I was in Japan. This work, we proposed two approaches since the collection is even more larger here, and then you have not one timeline but a couple of them. We couldn't have any supervised solution, and LLMs were not popular at that time. So we employed two simpler solutions. One was called divide and summarize. The idea is that you divide this collection into some topically coherent areas, clusters, and then make a traditional TLS from each of them, timeline summarization. The other was actually a better approach. Our proposal, two-stage affinity propagation summarization, where you extract events, only events, then you do linking between events and generate summaries. Again, there was no need to set number K of timelines. Also here, no need to say how many timelines we have. This is what should be calculated. And I will focus on this two-stage affinity propagation approach, which I call extract and connect. And there were two stages. So in the first stage, well, there are some assumptions we did, but that's actually not so important, is that there is some retrospective mentions of past in the news, obviously there is, and then on similar dates, sentences or mentioning similar dates have higher probability to refer to same events, obvious things. But how we clustered first, sentences is based on how similar they are. So this is consign similarity, a simple embedding to embedding vector score, comparison score, which tells how much this sentence is similar to that. But we also consider time. Are these two sentences referring to the same time or not? We extracted dates from sentences using, and some other temporal expressions using temporal tagger, as I mentioned, and then combine these two similarities, temporal similarity of two sentences based on their timestamp, and content similarities of sentences based on their vectorial content representation. Well, this similarity was just looking into distance under exponential decay. This one, as I said, cosine over BERT vectors. BERT was used to represent sentences. You can get a vector for using sentence verbs, obviously. And then we cluster it using, it's not mentioned here, using affinity propagation. And this is very nice clustering algorithm for the reason that you don't need to set the number K of clusters to make, because we don't know how many timelines are there. Then it is just itself finds a good number of clusters, depending on the data, right? So in our case, this was finding events because we grouped sentences, each of them with certain date. If they refer to the same time and if they have similar content, then they were put together. And this is based on a message passing algorithm, this clustering. So that was the first stage. And we later further filter out some clusters based on salience and consistency. If the size of cluster is very small on logarithmic processing, then we dropped such clusters. Maybe the event was just not important. It's not referred. And then here, based on cosine similarity, so how coherent are the semantically, sentences within a cluster, and use some thresholds to remove those. And then finally, second stage affinity propagation was based on linking the events. So now cluster is considered as an event. We move on in a pipeline and we do this here. So we basically connect events to build a timeline and looking how often the two events on the timeline are referring to each other. So one event should refer another event, then should be on a timeline, and also how similar they are. The sentences in one event should be somehow similar to the other event. Like that's the case of apple versus fruit and apple versus company. this second part would be very useful. And here, the first part would be useful. Perhaps are we talking about CEOs or about products or acquisitions or some events related to company? With parameter here, of course. So this was done in a second stage, and then we remove unimportant timelines, which were just having not that good coherence in terms of similarity. How strong you want to apply this threshold is again a matter of some parameter. So you can maybe even skip this step and show everything to the user. So anyway, all these generation stages using simple mathematical equations and clusterings, not too hard, can be computed cheaply on a large amount of data. Well, you still need to cluster things, which is the most time consuming, but okay. And then we use two data sets. The problem is that this is a new task. We didn't have a data set for multiple timeline summarization, but the ones for individual timeline summarization. So how to evaluate was the problem. And what we did, we basically, this is the same, we basically combined data sets. Let's say you take all articles from an Egypt data set together with Libya to form another data set where you know you should have two timelines generated from that, right? Or even more complex case, you combine all of these and you know that you should generate 5 timelines, right? You just synthetically combine data sets, creating your own multi-timeline summarization data set. But now the evaluation is even more harder, how to evaluate things. We already know how to evaluate timeline by system and the ground truth timeline, but what about multiple timelines by system and multiple timelines, ground truth timelines, right? It's harder. So we did a matching. The best timeline here matches to the best timeline here, and then the next one and the next one, right? To only compare timeline to timeline, not timeline to multiple timelines, right? So one-to-one we did by this matching. Some details are there, but actually you find most similar timeline in the set of system timelines based to the particular timeline in the ground truth. And then the same approaches, because you have now one timeline to one timeline, were used a couple of methods, TLS methods, data segmentation ways, randomly LDA, so topic modeling, k-means, everybody knows that, and our proposed model. And basically we could find quite good achievements. Maybe this is interesting. Do we really need MTLS was the question. If we have just one data set which has pure documents on one topic, then we really don't need all these complex operations, because our timeline will be worse than you would employ existing system for just TLS, right? For a different TLS solutions, we employ 3 methods. But if you have already a couple of mixed data sets together, and then you employ just one TLS and use this one timeline, you dramatically drop the accuracy. So it means you really need to do something more if you have such a dirty timelines and you want to actually create, dirty data sets, and you want to create a couple of timelines. And then our method was performing best over different data sets. A lot of comparisons, which I skip here, they are just details and the effect of parameters. We have many parameters, so we studied them in a detail. What is their effect on the quality? And here's one generated timeline for the case, maybe the second one I can focus. When you combine a data set like from this disease, another swine disease, and a flu, it's a hard case, how to generate 3 timelines for each of them separately. But I think it was not too bad, at least. So these are the good timelines, examples. And here is the bad timeline, where you put Iraq content next to Egyptian but unrelated things, and that's not what we would like to have. So it was a bad example. Application of this multiple timeline summarization. So we think it is a way to improve news search also. You have these news retrieval engines. You can type a query And then you typically would have just news articles in the relevance to the query, ordered by their relevance. But maybe that's not the best way, because let's say you don't know much about it, and then this may come from any year in the past, then some other year, you don't have this big picture. It is just based on relevance, and that is maybe not the best. Much better would be if we generate such multiple timelines and maybe treat this one as a retrieval, not each article, but this as a retrieval, and they could be ranked. So retrieve, summarize, and rank the paradigm. They could be ranked by whatever way. We could somehow consider coherence here, the number of events, not only just relevance to the query. And perhaps more realistically, rather than just using it as the final output, use it as a stepping stone to to better select the news. So you have these events, you can click on some time here, maybe here, and then read the news. But you have this helicopter view, you have overview, and you can maybe better decide what news articles you want to really read for a given query. This is much to be studied more, because different types of queries may demand different solutions. It doesn't have to be just name entity. It could be a precise event here you ask for. Well, then maybe we don't need that all, or perhaps we still need. This is to be studied. As I said, news ranking is just working in the same way as page ranking, but it's somehow against intuition, because you have so much time factor here. You have so many relations between different news. Perhaps a different style of search could be researched. So many points for the future: how to generate timelines, evaluate them, how to rank them, label, perhaps even you need some short label, and how to maybe provide some interactive solution for using such a tool. I'm just checking the time, but we still have a couple of minutes. And so I will quickly introduce, maybe, I think this will be like 5 to 10 slides on this one. And then I will leave the last for tomorrow. Plus, of course, tomorrow we'll have some other topics. So I want to talk about timeline document summarization. It's a new variant. It's the case where you have a document that in itself is a timeline, right? So a document is already a timeline. If I take this Salzburg and Innsbruck Wikipedia pages and maybe zoom only on history sections, well, this will be already a timeline. You will have a sentence, a date here and there, another sentence, date. You can just extract them with dates and treat it as a one timeline, another timeline. And now perhaps I want to summarize the timelines, not summarize original news article collection, but summarize the timelines. That's why we call it timeline document summarization. And one may ask, why do you need to summarize different timelines? Well, perhaps I want to find a typical Austrian city history, right? Or typical Indian city history, or something like that, or typical biography of a football player in the 1990s, right? That was perhaps from Brazil, and so on and so on. So it's still kind of useful, this. Especially if you consider even just Wikipedia, you have many entities with many timelines, biographies, histories of cities, countries, whatever, companies. And then you have many categorizations present, right? So you have Indian companies, Indian metallurgy companies, Indian cities, right? Indian poets, whatever, in this century, and so on. So we can create such a timelines, answering questions from the user. What's the history of Japanese city? What's the typical life of American scientists in 19th century? And so on and so on. And this is example summary for a Japanese city. Of course, if you click on it, you get more information. There is a year, average year over different cities where battles happened. Major revolution was in many cities. It is a number of cities that actually have an event described by this cluster, and here is an average date, right? So you kind of see a confidence for each event, a short label, and meantime when this happened. And that is kind of making sense because there was a war here, there was many kind of samurai battles in Japan, there was investment in transportation, in nuclear plants being established, there were many earthquakes recently, and so on and so on. And how to create this summary? Well, here is a way to create it. So you have two ways, basically. One way is maybe I will look into right side first. Out of all these timelines, you pick up one that is most representative, right? It's kind of extractive. Pick up one timeline and say, that is a typical history of Japan, right? Look at this city or typical biography, or let's say Indian Bollywood actor, right? In this recent decades. Another way would be you pick up some important events and then combine them to create a so-called prototype rather than exemplar. The problem here is that here you will have nice coherence, everything nice, but here you will have here and there apple and oranges, and if you don't do well pre-processing, you might have even some conflicts, saying that he divorced first, but was not married before, and so on and so on. But on the other hand, here we have more flexibility to picking up stuff than just here. So different approaches. We used kind of topic modeling at that time, and I will not go so much into detail here because my goal was just to signal the kind of task here. But I just want to say that we also generated in a contrastive fashion, let's say typical Chinese history versus typical Japanese city history. And then it was quite informative because generation of one timeline is depending on how the other timeline was generated. So it's not separately done. Again, some kind of topic-based clusterings. We did a lot of processing here. And the last point I maybe want to say is that we may also not be able to know these types, right? Here I say Chinese versus Japanese, right? But let's suppose I have all bunch of Japanese cities and I want to have some comparison, but I don't know what group should be compared to what group. These are just cities, 550 of them. So we did a very complex clustering way to find similar histories, and then from similar histories make a average timeline. Like here, so we input 550 cities, and using affinity propagation, which can find its own clusters, number of clusters. We had 3 clusters or 3 timelines. One is the largest number of cities in Japan. The other are historically traditional cities like Kyoto. And the last very small group of only 2 cities, 3 cities actually, was the cities in Japan that collaborated with the West, that have some trade. And Japan was locked for many centuries, and no trade was permitted, only to limited extent. So very different cities because they had open to the West, basically, trading. And this was automatically done, basically, all these groupings, and the timeline was generated for each cluster, also in a contrastive fashion, so that's a lot of things here. And then we think this is even more informative than doing one timeline, and that's it. Okay, I will skip here. We have a couple of minutes, well, few, because we still need lunch, to, let's say, take any questions or comments, if there is any. Otherwise, we can, of course, continue tomorrow with a couple of minutes before and discuss anything that you want to ask. I can later talk with you about your question, maybe if you are not in a hurry to go for lunch. But to the others, if there is anything I should repeat, let me know. Sorry for a lot of talking. I should be more asking students, perhaps. Just there was too many slides, but we covered that. And tomorrow will be little bit finishing of these different temporal summarization styles, but not many. I would say maybe 20% slides are left. And the other topics will be question answering and information retrieval. So different things, but temporally focused. And from now on, only temporal focused things. So anything that we should clarify? Anything you want to discuss? Is that fine? Okay, so I don't see any. I don't hear anything on the online audience side. I think we will then finish. Wishing you a nice day, and as Rakhavendra said, there will be another lecture, right?
Yeah, from 3 p.m. ma'am will start 3 to 4, and then 4 to 5, Shubham will take the.
All right, thank you then.
Tomorrow would be the closing ceremony.
Okay. So let's have a break, a lunch break. We can talk a bit. Well, break before the next teacher, right? From what time is it?
3, so from 3 5 will start.
Okay.
What are you guys doing? The working systems.
Yeah.
I do think so. This time. So it's a short term and you specify that this time, and then we'll watch. That's right. What is the sort of time? Like first beginning then. Like some family. Of that guy. We can do some. And this is that the government is moving by those. We have systems which they are doing this. So when command comes, so you have technical parts also. When I'm saying you have to go there, not the ones. You have to reach that. The time of it can be anything. Like maybe minutes, maybe. So